Hello, everybody, and welcome to Physics 152. This week, we're going to be learning about electric field and electric charges and how those things work together. A lot of this information is in the handout for problem number 1 and in chapters 25 and 26. I wanted to make a video talking about some of these concepts to help you understand what's going on. First thing that you need to understand is really what is an electric field. Well, an electric field, what does that mean? It means that at every point in space, there is a vector. What does that mean? Well, let's imagine I'm at this location and there would be an electric field pointing this direction. At another location, say here, the electric field might be pointing in that direction. At another location in space, the electric field might be pointing in that direction. What does that mean? Well, the electric field tells us the following. It tells us the direction that a positive charge would feel a force. So if this were our electric field here, and I were to put a positive charge here, that positive charge would feel a force in that direction. If I were to put a negative charge right here, that negative charge would feel a force in that direction. That'd be the force in the negative charge that way. One of the really interesting things about electric field is we don't know what produces it. Meaning we know positive charges and negative charges make field, but if you were to just measure a field in space, you wouldn't be sure what it came from. So for example, if I put a positive charge over here, you could think of it creating an electric field pointing away from it. In general, a positive charge will always create an electric field that points away from it. Your textbook has much better illustrations than I do. And a negative charge will always create an electric field pointing towards it. Okay. However, if you just have one measurement, say this measurement, you don't know if it's a positive charge here or if it's a negative charge here. So the electric field doesn't really care whether it's positive or negative making it. It's all going to be doing the same thing. And that means that positive versus positive charges will feel repulsive forces on each other. And negative charges will also feel repulsive forces on each other. But positive and negative charges will feel attraction together. And that's really what we're learning in this week's material. I'm going to mention this because you can't hear it enough times, even though you don't know what it means yet. The direction of the electric field, meaning the direction of that vector, also tells you the direction of decreasing electric potential. We're not going to learn about electric potential until week 2, but the number of times I can get this in your head, the better. There are two things that E field tells you. The first is the direction that a positive charge would feel a force, and the direction of decreasing electric potential. All right, so let's look at now how do we draw the electric field and how do we make sense of the mathematics behind it. So let's say I have a charge Q1 here, and I tell you that around the charge Q1, this is what the electric field looks like. So the first question I have for you is, are we looking at a positive charge or a negative charge? Well, because we know this is where the charge is located, and we see the vectors are going away from it, we can conclude that Q1 is positive, because what we say is that Q1 creates electric field pointing away from itself. So what does that mean? If I were to put a positive charge here, it would feel a force that direction. That's what we mean by that. And then, if you look at C and D here, what you see is that the force vector here, or the electric field vector here, is larger than the electric field vector there. So if I were to put a positive charge here and that same positive charge there, they would each experience a force. However, the force created here would be larger than the force created there. Now, why is that? Well, as it turns out, the electric field is said to be an inverse square law. What does that mean? Well, it means that the strength or the length of that vector is equal to this constant term, which sometimes is called K, times the charge that's creating it, divided by the distance squared. So that's what we mean by inverse square law. So let's imagine I'm trying to figure out, well, if I put the electric field vector here and it's 2 units long, and I want to compare it to the electric field vector here, and I want to know how long to make it, well, how do I make that decision? How do I come up with what that length should be? So what we need to do for that sort of thing is to create a ratio of the electric field strength at B versus the electric field strength at A. So that really just means, well, take EB, use this formula to create a fraction. Now, I recognize a lot of people will see that fraction and go, oh my gosh, what's going on? But the beauty of creating a ratio is that all the terms in common cancel out. All the things they share go away. And what you're left with at the end of the day is just the difference. So the only difference between point A and point B is how far away they are from the source charge. And I realize that all of my charges are shifted just a little bit, so I'm going to move these over just, there we go. So what's going on here? We've got 3 units to A, and we have 6 units to B. So we're now going to say 3 units. Now the beauty of creating a ratio is I don't know if this is meters, maybe it's feet, maybe it's inches, maybe it's millimeters, I don't know. It doesn't really matter. Remember, the ratio gets rid of all the things that are in common and leaves only the difference. So whatever that actual unit of measure is will go away because that's in common to A and to B, leaving only the actual distance ratio apart. So when I plug those in, I'm going to get 1/4. So that means that I'm going to go twice the distance, right? 3 versus 6. I actually drop strength by 1/4. So that's really what an inverse square law is saying. So the ratio of B to A is 1/4. So if this one is 2 units long, this one should be a half a unit long. So next, what about point C, right? You might see that this one looks like it's 2 boxes long, and this vector might look a lot shorter to you than it should be. Well, as it turns out, it's actually right. Now, why is that? Well, if you do the distances EC to EA, again, you're left with only what's different. And now we're looking at a triangle that's 3 long with a square root of 2 added on there. And when you do this ratio, it turns out to be a half. So that says the length of EC should be a half of EA. Well, if you look here, EA is 3 units apart, so it's 2 long. Well, at D, that's 3 units away, so that should also be 2 long. So now if you look here, this is 2, and this point should be 1/2, which means it should be 1 box long. But remember, the full length across is square root of 2, so 1 long is actually only going to be about that far. So we see that, anything that's basically on the circle away is going to be 2 long. But if you're this much further away than the circle, that extra distance causes you to go from 2 units long to 1 unit long. So when we say inverse square, what we're really saying is that the field drops very quickly as a function of the square of the distance. And that's how when you go from 3 to 6, you drop by a factor of 1/4. When you go from 3 to 3 root 2, you drop by a factor of 1/2. So we don't expect you to memorize these terms, but we do want you to recognize that inverse square does mean a pretty fast drop. All right. So let's look at the complication of having multiple charges. So now let's imagine I have my Q1 again, which we've already realized is a positive charge. And now I'm going to add a second charge, Q2. Pardon me, I realize that these are off just a little bit on their alignment as well. There we go. All right. So now I've got Q1 already drawn, and now I have Q2 that's going to itself make its own electric field. So now I'm going to draw one vector for Q2. If we look here, that vector at 3 boxes away has a length of 3. So what's bigger, Q1 or Q2? Well, at 3 boxes away for Q1, you get an electric field that's 2 long. At 1, 2, 3 boxes away for Q2, your electric field that's 3 long. So Q2 has a greater influence. Now, what sign is Q2? Q2 is also going to be positive because it's creating electric field pointing away. So you might ask, well, what do you do now? Do you just draw 2 vectors at every location for each of the charges? Well, you do when you're maybe first figuring it out, but that's not our goal at the end because that's going to be really confusing and not exactly physical. We're going to use what's called the principle of superposition, which is a fancy way of saying you add up the vectors. So what you would do at all the locations that you found interesting is you would draw a vector due to Q2, and then you would add that to the vectors due to Q1. So let's do that. So now at location B, we have our electric field from charge 1, and we have our electric field from charge 2. Let's see, hold on here. My computer decided to not cooperate for a moment. There we go. So we then add those two vectors up. So I draw my vector from 2, and I add to the end of it my vector from 1, which leaves me with the combination vector there. So that means the total electric field at that location is this 2-unit vector here. Now, just to note, these vectors should technically run on top of one another, but it's really hard to tell what's going on. So I've drawn them just slightly offset for that reason. And it's okay if you have two vectors that look like they're crossing like that, because what a vector is only telling you is what is the location of the electric field at this location. So that means this long. So if I draw another vector here and it looks like they cross, that doesn't mean anything physically. It's just this is the electric field at that location, and this is the electric field at that location. So the crossing doesn't actually mean anything. All right, so then we look at location A. So we come up here to location A. And at A, you see that 1A was too long. And then we realize that, okay, 1, 2, 3 is how far away this is. So at A, that's 1, 2, 3, 4, 5, 6. So we know that when I double my distance, I quarter my field. So then 1/4 of 3 is going to make this little shorter guy here. So when they add up, they look like the following. So I'm not expecting to follow all of this super quickly. I'm trying to give you an example of what things look like. Imagine that I've compressed the lecture that would have lost you into a very short amount of time to sort of get you started for what we're going to do in class starting today and throughout the week. So now what do is we go back and we begin to draw, instead of the individual vectors, we draw the superimposed vectors at those locations. And here you see like these vectors appear to kind of run over one another. And I've drawn them just slightly offset from each other because I'm trying to make it clear that they are different vectors. It really doesn't matter if the vectors hit because, again, they're only telling the strength of the field at that location. So how would this have changed if Q2 was negative? You know, how would it have mattered if that thing had a negative charge instead? Well, you would just go back up to this image, and at this location, you would now have a field going that way. So that when you added this to this, you would have something longer. And you're going to get that practice this week as you work on these sheets. So what I want to talk to you about now is what happens when you have not just two charges you're adding together, but you have 10, 20, 30 charges that you're adding together, or what we call charge arrangements. So now let's imagine that we had something that looked like the following. We had a whole bunch of charges, all the same sign, all arranged in a line. What we're going to see is that this is useful if you want to think about what we call a plane of charge. So think about a whole bunch of charges arranged something like this. Okay. It's also helpful if you want to think about, say, like a wire full of charges as well. So now what does this look like? Well, what you have to do technically is go through each and every single charge and draw electric field vectors. That's going to get pretty tedious, right? So let's just do a couple of certain cases. So now let's imagine I want to know the electric field at this location near all of these arranged charges. So at this location, I'm going to draw this electric field as such. Now what am I going to do? I'm going to say, okay, what's the electric field contribution from the purple one? And I see that this purple one, by symmetry, is going to contribute the same kind of thing. Well, my distance is now √2 compared to 1. So I know that whatever effect I get here is going to be half of whatever effect this one gave me. And so this plus charge here in the center was about 2.8 long, which means that I'm going to get about 1.4 now, because that's half for this one. And so that's what we get as a diagonal. And those numbers were chosen on purpose to work out. So now this positive charge and this positive charge are going to contribute like the following. And then if you work out carefully the trig here to get what that distance is, you would get a vector about this long. And the same thing here. So we can see that we can build the field vectors at each location based off of the charges in their arrangement. And I could keep going and do the orange ones and then whichever ones are over here. But you can already see that they're starting to have vanishingly small contribution there. So now the question is, what does the electric field look like at that location? Well, it looks like whatever you get when you add up all of those vectors. So let's do that carefully. So now what do I have? I have that vector here from the red. I have the two purple ones. I have the blue or green ones and the black ones, etc. And when I just go through the process of putting them all tip to tail, etc., I'm going to get some combined vector that looks like that. So I come back to this picture, I'm going to get some combined vector that looks like the following. And then I think you can understand that if this pattern of charges just keeps going everywhere, at this location, I'm going to get another combined vector that looks something like that. And here, a combined vector looks something like that. So what we're seeing is that unlike a positive charge that has electric field vector spreading out everywhere, right around it, when I begin to pile them up in a certain way, their collective behavior is to create an electric field that's kind of going in one direction. So unlike that point charge that's sort of spreading, we're now getting something that isn't spreading. It's now going off in one direction. And so if this collection of charges were just on a wire, meaning it looked just something like the following, that field would be spreading out. And if we were to look just say down this direction, so we're just looking on the pipe side of it, you would get the field is just spreading out radially again. But it's not spreading out in the same way that a point charge did. So this kind of looks like a point charge, except it's coming out like spokes off an axle in all these different directions. And your textbook has such better pictures than I have. And the cumulative effect of this is we're not going to do much with in this course, but I want you to see this, especially if you're thinking about studying physics beyond this. The electric field from this line of charge can be found as this lambda over 2 pi epsilon r. Now, why is that interesting? Well, that's interesting because instead of this now being an inverse square law, it's just a 1 by r law. And this lambda is just charge per length, so this is like a linear charge density. So let's now look at the system that we're going to actually find interesting in this course that we're going to study more of, and that is a plane of charge. So now the plane of charge is not just a bunch of charges in a line, but it's charges arranged up and down in a plane. So think of a sheet of paper, right? And that sheet of paper is charged everywhere. And then if you look at a small little area element on it, that charge per area is what we're going to call eta. Again, this is eta. A lot of people don't know the Greek alphabet, so there you go, that's eta. And what you're going to see here for that electric field is it's eta over 2 epsilon naught. And this epsilon naught you'll see in your textbook is based on how hard it is for electric fields or how easy it is for electric fields to pass through a vacuum or air. Right? So for us, it's basically the same thing. And what you're going to see there is a lack of distance dependence, right? Whereas a point charge was q over r squared, and a line of charge is basically q over r. For a plane, it's q over no radial dependence at all. And what does that mean? Well, it means that if you look side on at a plane of charge, that there's no distance dependence on either side, so that the electric field shouldn't matter as you move away from it, as long as this distance is small compared to the extent of the plane. And again, your textbook has so many pictures of this that are so much better than what I can draw in this format, but I wanted you to just sort of get some words breathed in there. Here it said, it sometimes makes it a little bit less confusing to read. Please ask questions. This material is hard for all students this term, largely because none of you have taken physics with electromagnetism before, and so it's all new. And then if you look at this, the math is starting to get a bit harder than stuff we've done before. So we're going to continue as we did before. It's going to be one step building on top of the next step all term. But because it's new for everyone, we're all going to have to work a little bit harder to get there. And we've modified the course a little bit to help with that, going down to 4 people per session instead of 6 people per session. Thank you very much. Ask questions as you have them. Bye-bye.